Okay, now we're coming to look at drawing a table of all our data. As you can see, I've already filled in a number of the values into the cells, but I want you to spot one or two things before we actually start. The range over which I've taken the values here is as large as possible within practical limits. So with the particular set of apparatus I had, I could vary between 10 and 40 volts. You should generally try to make sure that range is large. You should also make sure that you've got a relatively large number of readings, and by that I mean probably 7 or more. So if you're actually doing the experiment, make sure that you've got at least 7 readings in a reasonably large range. Now if we come on to look at the table in detail, there's one or two things that I hope you've spotted already are missing. The units in the column headings are all missing, so you must make sure that you put those units in there. So I've been measuring the potential difference here in volts, so I'll represent that as potential difference in volts. The current setting I've actually taken 3 readings, and I'm going to calculate a mean value. All of these are actually in milliamps, so I must make sure that in every column heading I've actually put this as my unit. Now we come on to looking at the resistance. What's going to be the unit of resistance? Well, if we're going to calculate this, we're actually doing volts divided by milliamps. So if we do volts divided by milliamps, that's the same as saying volts divided by 10 to the minus 3 amps. Now if you put this into your calculator, 1 over 10 to the minus 3, you'll find is exactly the same as 10 to the 3. And we already know from our lessons that volts divided by amps is the ohm. So the unit that we're going to have for our resistance measurement there is 10 to the minus 3 ohms, or something that we would usually abbreviate to kilo ohms. In a similar way, our power calculations that are going to be the potential difference multiplied by the mean current is going to be volts multiplied by milliamps. And we know volts multiplied by amps is watts, volts multiplied by milliamps is milliwatts. Make sure you get the units right before you do anything else. Now we've taken all this data, and you can actually see here that what we've done is taken the data to the precision of the instrument. On this occasion here, my instrument was just reading the potential difference to the nearest volt. The current, however, was being recorded to the nearest 100th of a milliamp. Now when we come to calculate the mean value, you all know that what we need to do is add the 3 values together and divide by 3. Sometimes you'll come out with numbers that look quite nice. 1.94 is the answer there. So that is to the same precision as the values that we've taken here. However, other values, like the next one down, your calculator will probably tell you that the mean value there is 2.71666 recurring. You must write that down to the same precision as all the other values, so that's 2.72. One other one to be aware of is this one down here. If you put the numbers in your calculator, again the display on the calculator will say that the answer here is 4.9. However, again, you're taking care to make sure that all the data in this column is to the same precision. So you must put a 0 on there. And let's just do the bottom one down there. The number there comes out to be 7.44. So that's the mean value that you've calculated. Now you need to work out the resistance. You might question, how many decimal places am I going to put here? Well, probably the best approach when we're doing calculated values is that the numbers in these calculated columns should be roughly the same number of significant figures as the values that you've used to calculate them with. So when we do the resistance, potential difference divided by the current, we should actually do this one here that's 2 significant figures, this is 3 significant figures. So which do we choose? On this occasion we generally round up. So the answer that we would get here would be 5.15 kilo ohms. And all the way down here you should find that all these values are very similar. So the value of the resistance there is 5.37. This is because the instrument, the piece of apparatus that is being used, is a single resistor. However, now we come on to the power calculations. When we look at the power calculations, do the top one, and writing it to 3 significant figures, we would say that the power here is 19.4 milliwatts. However, if we write down the one at the bottom, put the numbers in our calculator, and we should find that this comes out at 297.7. Now some of you might be looking at that and thinking, what do I do here? I've started off with a value at 3 significant figures. I've ended up with a value at 4 significant figures. Should I leave it like that, or should I put them all at 3 significant figures? Well, the important idea when you're drawing a table is that when you look at any column, that includes this one here, all the data should be to the same precision. So if I'm doing this value with a precision of 0.1 of a milliwatt, this value at the bottom should also be 0.1 of a milliwatt. And if you left it like that, that would probably be okay. However, you might look finally and say, well, if I look at this number here, I've reported that to 4 significant figures, and I've calculated that from a number with 3 significant figures and a number with 2 significant figures. So that is probably too precise based on the data that I've used. So if I was being really careful on this one, making sure that I got the full marks, I'd probably just report that one at 2.97 milliwatts, which would mean that I would need to report that top one there at 19 milliwatts. They need to be the same precision in each column of the data.